Magnetic flux. Let's review a bit. Gravitational field lines originate at infinity and terminate on masses. Electric field lines originate on positive charges and terminate on negative charges. Magnetic field lines do not originate or terminate anywhere. They are visualized as continuous loops, which doesn't mean it's a circle. It just means that it's a loop. Anyway, for this reason, the net magnetic flux through any closed 3D surface is always zero. If you have a three-dimensional surface, the flux will be piercing in at one point, and because it's always a continuous loop, it has to pierce out at some point. So if you have a closed 3D surface, the net magnetic flux through that surface is always going to be zero. In general, the electric flux is equal to, we ran into this a long time ago, E dot dA. And if we're starting and ending at the same spot, then we would put maybe a little circle here to indicate that on the integral sign. But if we don't have a closed surface, we can leave that off. But in any case, it's a similar equation for magnetic flux. And once again, if we have a closed surface and starting and ending our integration at the same spot, we might put a circle right there. Two units for magnetic flux are Tesla meters squared. That's one of them. And another one is the Webers, which has the symbol capital W, lowercase b. For any closed three-dimensional surface, like a sphere or a cylinder that has an inside and an outside, the physics community has defined that dA elements point in which direction? Point outward from the surface. And at what angle? Perpendicular, 90 degrees. So we're going to see that here in these pictures. You can see that we have a little dA element, and that dA element, which is indicated by the window pane, has a direction that points at 90 degrees to it. Which diagrams show positive flux, negative flux, or zero flux? Zero flux is going to be number 2 here, because you can see that the magnetic field lines are not poking through the surface. They're just scraping the surface. So there's going to be no magnetic flux there. Number 1 is going to have positive flux, because the dA element and the B field lines point in the same general direction. And actually, number 3 will also have some positive flux. Now, it won't have the same amount of magnetic flux as number 1 will, because there's an angle that has to be accounted for here. But none of these figures are showing negative flux. Let's do one problem here. We want to derive an expression for the total magnetic flux through the rectangular window shown. Incidentally, the window need not have conducting boundaries. It could be made out of plastic. Or there doesn't even have to be any material on the perimeter of that space at all. It could just be a rectangle in empty space that we are giving imaginary boundaries to. So what we want to do is we want to find the magnetic flux here. And in general, the magnetic flux can be found by integrating the magnetic field with dA, the magnetic field that's going through this loop. Now, what is the magnetic field that's going through this window? Well, it's due to the current that's flowing through this wire here at the top of the page. And the magnetic field, you might remember, due to a current carrying wire at a radial distance r, is equal to, down here at the bottom of the screen, mu naught I divided by 2 pi r. The deal is that r is going to be varying for different bits of this window. So what we want is we want to define a bit of this window, a little dA element of this window, such that each part of that little dA has the same value of the magnetic field. There's the distance r right there. The thickness of this is dr, the thickness of this little strip here. And this little strip, that's a dA right there. Now, why are we doing this? You remember that close to this current carrying wire, the magnetic field is going to be strong. The further away we get, the magnetic field is going to be weaker and weaker. So what we need to do with this window is we need to break it into little tiny strips, and we need to find the total magnetic flux for each of those strips, and then we're going to add them up. That means in our little integral down here on the lower half of the page, we're going to integrate this from, you can see the diagram, from r equals a, that's where the first value r is going to start, and we're going to go all the way up until r equals b. And what's dA? In terms of our diagram, isn't it L times dr? See, dA is a little tiny rectangle which has the area L, which is given in the diagram, times that tiny little height, which is dr. If we simplify this, what does this give us? Let's pull the constants out of the integral. Mu naught is a constant, L is a constant, I is a constant, 2 pi is a constant, and that just means that we are integrating from r equals a to r equals b dr over r. And when we integrate that, that's going to give us the log, isn't it? A natural log. So I think the final answer that we're going to want here looks like this. Mu naught times L times I divided by 2 pi times the natural log of b over a.